Hi, in this video, I will be showing you problem number 11 of chapter 15, section 4. A lamina occupies the part of the disk x square plus y square less than or equal to 1 in the first quadrant. Find the center of mass if the density at any point is proportional to its distance from the x-axis. So underline the keywords. So it occupies, it's a part of the lamina is part of the disk x square plus y square less than or equal to 1 in the first quadrant. So that's an important clue. Find the center of mass if the density at any point is proportional to its distance from the x-axis. So if xy is a point in the first quadrant, then its distance from the x-axis is y and its distance from the y-axis is x. So this is going to help us to find out the density function. Before we first write down the formulas for to get the mass of the lamina and the moments about the x-axis and the center of mass. If a lamina occupies a plane region D and has density function rho of xy, write expressions for each of the following in terms of double integrals. The mass M equal to double integral over D rho of xy, the density rho of xy, dA or dy dx. The moments about the axis, first we will write down the moment about the x-axis, which is m sub x, is equal to double integral over d y times rho of xy dA. And m sub y, which is the moment about the y-axis, is double integral over d x times rho of xy dA. And the center of mass is denoted by x bar, y bar, where x bar is my over m, y bar is mx over m. So center of mass is for this thin plate is is a point where the plate gets balanced. So let's now write down the function rho of xy. It says that it is proportional to the distance. Rho of xy at any point is proportional to its distance from the x-axis. So for this point xy, distance from the x-axis is y. So rho of xy being proportional to this distance, so it is k times y. Then now m mass is double integral over d rho of xy dA. So rho of xy is ky. So this will be the density times dy dx. So it's theta. So suppose we convert everything to polar coordinates. Then we get theta running from 0 to pi by 2. The reason it is pi by 2 is that the lamina is in the first quadrant. So lamina is given to be in the first quadrant. So r runs from 0 to 1 and theta runs from 0 through pi by 2. K times y gets replaced by r sine theta. Then dy dx or dA in polar is r dr d theta. So now we'll evaluate this. K is a constant which can be taken out. 0 through pi by 2 sine theta d theta times integral r varying from 0 to 1 r squared dr. Note that it is a separable function because theta and r are definite limits, and also one variable does not depend on the other. So it's a polar rectangle. So it's k times negative cosine theta between 0 through pi by 2 then r cube over 3 between 0 and 1. So if we plug in these values in the upper limit and the lower limit, and then we use definite integral property. So it's k times 1 times 1 over 3, which is k over 3. So that is the mass. Now let's find out mx and my. My is double integral over dx times rho of xy dA. Rho of xy is ky dA. And then if we apply the polar coordinates here also, it is r cosine theta times r sine theta. K is taken out of the integral sign. Then dA gets replaced by r dr d theta. So it is k times integral 0 through pi by 2 for theta. Then integral 0 through cosine theta, sine theta, d theta. Then integral r varying from 0 to 1, r cube dr. This is again separable function. Function of theta times function of r. So you can separate the integral and multiply the way we have written. So here you can either apply u sub, or you can substitute u equal to cosine theta and do the problem, or you can also do write this as sine of 2 theta over 2 and then integrate. So whichever method you do, it is k times 1/2 of sine square theta 0 to pi by 2 r to the power 4 over 4 0 to 1. Here I have substituted u equal to sine theta. Then my, the moment about the y-axis is k times 1/2 times 1/4, which is k over 8. So we got my. Now we have to get the moment about the x-axis, which is m sub x, which is double integral over t y times ky dA. This ky is f of xy. So it is k times double integral r sine theta square times dA, which is r dr d theta. Then theta runs from 0 through pi by 2, r runs from 0 through 1. So m sub x is k times integral 0 through pi by 2 sine square theta d theta times integral 0 through 1 r cube dr. This is again separable function, so we are able to split the theta integrals and r integrals separately. So it is k times half angle formula must be used here. So 1 minus cosine of 2 theta over 2 d theta, then r to the power 4 over 4 integral between the limit 0 and 1. The k halves can be pulled out. Then it is integral is theta minus sine of 2 theta over 2 between the limits 0 and pi by 2 times 1/4. Simplifying and suitably substituting the limits, we get k over 8 times pi halves, which is k pi over 16. So we got m sub x, we got m sub y. So the moments are known. We got the mass also. So the center of mass, which is x bar over y, x bar comma y bar, which is my over m comma m sub x over m. If you substitute the respective values here, it is k over 8 over m, which is k over 3, which is mx, which is pi k over 16 divided by k over 3. Simplifying, we get 3 over 8, comma 3 pi over 16. Hope this video helps.